This is bad. Okay, if you stop looking at this,
Yeah, that might mean it's about to run out of battery.
okay, we'll see. Yeah, I don't mind using this.
Okay, sorry about that.
Okay.
Is the car just gonna smash into the? So I think we can go ahead and get started. So thanks everyone for coming to the A&C Seminar. We're really happy to have Shanthanu Rai, who's visiting us from the Caltech Institute of Fundamental Research in Mumbai. Shanthanu is a graduate student. He works on computational complexity, computer algebra, and various problems related to algebra and number theory in science. So today we're really happy to have him telling us about how to compute the polynomial in GCD with some really cool new algorithmic ideas. So Shanthanu, please.
Yeah. Thanks for the introduction, Robert. Yeah. So this is joint work with Mrinal, Varun, and Ramprasad from TIFR, and Somnath and Shivangi from University of Toronto. So feel free to stop me at any point if you have any questions during the talk. So the talk will be about the greatest common divisor, or the GCD, and we will be interested in GCD of polynomials. So the GCD of two polynomials is the largest, is a common factor of the largest degree. And I would like to insist that to define a unique polynomial as to be a GCD, that the GCD is monic. And today's talk will be about, can we compute the GCD of two polynomials efficiently, right? And we know this. I mean, this is like a well-known thing. So just like a quick refresher. So we know the Euclide's algorithm for GCD. Like for integers, what do? You apply the polynomial division with remainder multiple times until you see a zero remainder. And the last divisor you see would be the GCD. Right? And the same trick, same algorithm works also over polynomials. So that the polynomial division with remainder is, we have the division algorithm for that. So we keep applying it until we see a zero remainder. And the last divisor we see is the GCD, and I define it to be monic. So if I want to know like how long this algorithm runs for, so to explicitly write down what it looks like a sequence of polynomial division with reminders until I see a zero remainder. And at each stage, I know that the degree of the reminders I see will be less than the degree of the previous remainder. So in the worst case, the degree can reduce by just one. So this can happen for like d iterations. So number of iterations is d, the input size is d, the degree of both f and g, and the running time would just be d times the time for polynomial division with reminders. So this looks like something like d square time. And we also know that we can do this in near linear time as well, but for our purposes, this is like good enough. So, okay, once we know this, next, the main question I want to ask now is, okay, we have a quite fast sequential algorithm. Can you say something about like the parallel complexity of computing this? So this algorithm mentioned, the Euclid's algorithm, this looks very sequential. Like for computing the remainder R2, I need R1. For computing R3, I need R2. So there is like a dependency here. So if I'm going to ask about how do we parallelize this, it doesn't seem clear. Like at least looking at this like very inherently sequential algorithm, how do we do this, right? And surprisingly, by an awesome work of Robert and Avi Wigderson, we know that this is true. So what do we know? So they say that let f and g be two polynomials with degree at most d. Then we can compute the GCD of f and g with polynomially many processors and constant number of rounds. Okay. So here the emphasis on constant is important. So this means that the degree could be huge. It could be like 100, 1,000, whatever. But the number of rounds is constant. It doesn't depend on the degree at all. So if you like contrast this with the earlier algorithm we saw, this seems quite surprising. Like how is it? There is something interesting happening here. Okay. So I would like to now talk in the language of, rephrase this in the language of algebraic circuits, which will be useful for us in the talk. So let me define what algebraic circuits are. So an algebraic circuit it's like a DAG, the internal nodes being multiplication gates or plus gates. The leaves are variables or constants, and we compute the value, and we say that this circuit computes a polynomial by propagating these computations upwards naturally, like inductively. And for a circuit, for this model of computation, there are two parameters, resources or parameters of interest. These are the size and the depth. The size is the number of nodes in this circuit, and depth is the length of the longest route to leaf path. So comparing it with the language of parallel complexity before, the size corresponds to roughly the number of processors we have, and the depth will look like the number of rounds we have. Okay. So now if I wanted circuits for computing GCD, what I would like is something of this form. So if I'm given two polynomials f and g of degree d, let the coefficients be fd1 up to f0, gd1 up to g0. I would like a circuit that takes these coefficients as input and computes the GCD. So this triangle with this algebraic circuit, I'm just hiding the internal gates there. And what we want is, we want the size, which corresponds to the number of processors, to be polynomial in D. And we want the depth, which corresponds to the number of rounds, to be constant. Okay. And now let's rephrase the AW statement in this language. So what we have is, again, f and g are degree D polynomials. So the GCD of f and g can be computed by algebraic circuits of poly D size and constant depth. Okay. Here there is a minor caveat of this new term called piecewise. So it turns out that we need a little more than just algebraic circuits. We need this the power of branching. So we want so even in Euclid's algorithm, we wanted to check if the remainder is 0 at some point. So we need a branching instruction in our model. So once I add that small piece, this statement is true. Okay. I don't want to get it. So the next couple of slides talks about piecewise algebraic circuits, but I don't want to get into it. So if we want to know more about it, I will talk about it maybe towards the end. So I'm going to skip some slides. Okay. So, okay. Now we saw that GCD can be computed by constant depth circuits. I just want to talk about some other related problems that we know we can do in constant depth. Just a few of them. So we know that if I'm given two univariate polynomials, I can add them and multiply them in constant depth. So here the input size would be d, the degree of the polynomials, and I'm interested in circuits of size poly in d. So I know that I can do this in constant depth. I know that I can do division with remainder also in constant depth. This is a result of Binney and Pan in 85. And some other problems we know we can do is So I can do polynomial interpolation constant f. So given some alpha i's and beta i's, if I want to find a polynomial, the quotient of polynomial f such that f of alpha I is beta I can do this in constant depth. And maybe the last problem I'll mention is that we can do, so this problem of symbolic determinant. So if I give you a determinant, if I give you a matrix whose entries are variables xij, this I know that I can do it in log square depth. This is a result of Sankey. And I know that this we cannot do in constant depth. So it's an example of a problem which, so in contrast to GCD and the earlier problems I mentioned, so we have problems which we know we can't do in constant depth. Okay. Okay. So maybe now I'll go towards what our result here is. So Andrews Wigderson, this result, it is true over fields of characteristic 0 or 2D. So this last point in the star. And okay, they have this restriction because like a crucial component of their idea is the use of Newton identities. And that sort of does not work. I mean, that does not hold over small characteristics. So I'll talk about it a bit more later, but I would now let me state our result. So the result is exactly the same, just that there is no dependence on the characteristic. So it works over all characteristics as long as the field is large enough. Okay. 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 Maybe I will, at the risk of insulting my audience, I'll just define quickly what characteristic of a field is. So characteristic is just number of times I add 1 such that I get a 0 in a field. The characteristic of infinite fields is you can add 1 how many times, you'll never get a 0, so we define it to be 0. And characteristic of a finite field, for example, fp. So if I can add it 1p times and I get a 0, so it's p.
For example, like the characteristic is not too large, basically log is always
Yeah.
but the field size is large. Just to see where.
So we have fields of the form fp to the k. Yeah, so those fields it will not apply. Yeah. Yeah. Okay. So now that I've defined our results, so let me now try to give some ideas into the proof of this. So we'll now go over, so this is the result. So we'll go over some definitions that will be useful for us in the talk. So one is the notion of a symmetric polynomial. So we call a polynomial symmetric if its value doesn't change when I shuffle around the variables inside. Okay. And some canonical examples of symmetric polynomials are, one of them is elementary symmetric polynomial. So here, so the ith elementary symmetric polynomial would be I take subsets of size I, I sum of subsets of size I and multiply the corresponding variables in the set S. So just to be explicit, E1 of the first one looks like x1 plus x2 plus xn. The second one looks like this, x1, x2 plus x1, x3. And the nth element symmetric polynomial looks like x1, x2 into xn. Okay. Another symmetric polynomial that's nice is this power sum symmetric polynomial. So this is essentially I sum over all the variables and raise it to the ith one, for the ith power sum symmetric polynomial and raise it to the power I. Okay. And we'll notice one property of univariate polynomials and go into the some of the key ideas. So let f be some polynomial with coefficients fd minus 1, f1, f0. And suppose alpha 1, alpha 2 up to alpha d are its roots. Okay. So we'll make a simple observation that what does the coefficient of x power I looks like in terms of the roots? It essentially looks like an elementary symmetric polynomial. Right. So this fact will be good to keep in mind for the rest of the talk, that the coefficient of a polynomial is essentially an elementary symmetric polynomial in the roots of the polynomial. And we'll keep using this fact again and again. Okay. So now I would like to just give a very high level overview of what is happening in Andrews Wigderson. So this will not do justice. I mean, I will not go into a lot of details, but maybe just a very, very high level picture. So this is what we want. We have polynomials f and g, and we want to compute GCD of f and g in constant length. We want a circuit of this form. Now, let's maybe just do some visual thinking. Suppose we were given the roots of the polynomial, roots of f of x. Let's say the roots are alpha 1, alpha 2 up to alpha d with alpha d. Notice that x minus alpha will divide the GCD if and only if g of alpha is 0. So if x minus alpha divides the GCD, then x minus alpha is a factor of f and g, so g of alpha is 0. And if g of alpha is 0, then x minus alpha is a factor of the GCD. So it goes both ways. Okay, that's okay. Okay. So once we have this, so essentially what this statement says is that evaluating g at the roots of f gives me some handle about the factors in the GCD. So this gives me a high-level algorithm I could try, a parallel algorithm. What is that? So assuming f and g is square-free, I can compute the GCD by this. So I can compute g of alpha 1, alpha 2, alpha d parallelly. The non-zero values will tell me something about the factors in the GCD. So I collect these non-zero values and compute the GCD. This is very high level, but I hope at least the flavor of it is being conveyed, what's happening. So if there's any doubts, please let me know.
Sorry, could you explain why you have collected non-zero terms? So previous slide you said that g, like x minus alpha,
Oh,
has a GCD if and only g of alpha is 0.
sorry. Okay, 0 terms. My bad. Typo. Yeah. 0 terms. Then that gives me a GCD. Yeah. Yeah, but I'm assuming square free. Yeah, that's a good point. We can do something like this for square free, that also, but simplistic. Okay. So okay. I have not been very explicit in what I said, but I hope that like if alpha 1 up to alpha d, if the roots are given, then I have a parallel algorithm that comes to the GCD. At a high level, this idea is conveyed. Some sense. Okay. But then alpha 1 up to alpha d are the roots, and what I would like to get a circuit in the coefficients. Okay, that question is incomplete. So the question is, so given this circuit, can I get a circuit with the coefficients f0, f1 up to ft minus 1? And this is what like AW is trying to do. It's like playing the game of, okay, I have a small circuit in the roots, then how do I get access to something in the coefficients? And they sort of try to play this game. Okay. So now I want to make these ideas, this is a high level overlay. I want to make this ideas concrete. So I'll work with something simpler that's related to the GCD. So I'll work with something called resultant. For those of you who don't know what a resultant is, I'll tell you what it does first. So resultant is something, it's like an indicator for the GCD being 1. So resultant looks like, so if I take resultant of f and g, if GCD of f and g is 1, it will be a non-zero constant. And if otherwise, it will be 0. Okay. This is what resultant does. Now I'll define what it exactly is. So, sorry, before I define it, so just to set the stage, I will try to get a constant depth circuit for the resultant now. So this is what our task with the rest of the talk is. And the idea that are required for GCD are sort of very related to this. Okay. So, if we know, given to polynomials f and g, if you know that given that the GCD is 1, we can characterize this. So this is equivalent to saying that we have some Bezout coefficients a and b such that af plus bg is 1. And solving for this, a and b will result in a linear system that looks like this. So essentially, if GCD of f and g is 1, if and only if the determinant of this linear system is of this matrix is non-zero. Okay, this is a nice matrix with its entries in F's and G's, like in a nice, written in a nice fashion. And we define the resultant to be this determinant. The resultant of F and G is determinant of this matrix. Okay, and this characterizes when GCD of F and G is 1 or non-trivial. So now, and this matrix is known as Sylvester matrix. So now using this, let me try to construct a circuit for the resultant. So I know the resultant is a determinant, and I know that I know by Sankey's result how to get a circuit for the determinant. So using just that result, we get a log square m plus n depth circuit for this, right? But I want to shoot for something better. I want to shoot for constant depth. So what is it I'm not using here? Sankey result applied for any matrix, but the matrix I have is quite special. So maybe for this particular matrix, I might have more properties to exploit and get a constant depth circuit, right? So the question we ask is, okay, can I compute a constant depth circuit for this? Okay. And now we see the perspective of roots of polynomial coming up. So it turns out the resultant has another formula. So I'll state that. So if F and G are two polynomials, and let alpha 1 up to alpha m be the roots of f of x, it turns out that the resultant of F and G is this simple product. I go over all the roots of f and evaluate G. I mean, this is I'm not going to prove the lemma, but it's going to be a useful lemma for us. And to sort of get comfortable with this.
Sorry, is this the symmetric definition?
What do you mean with symmetry?
Is resultant of F and G same as resultant of G?
They are same modulus of -1 signs. It's a symmetric definition. So I can write this as product over all roots of G, f of the roots of G. It'll be the same thing with some sign difference.
And you're claiming this kind of a thing is true. So I can pick any polynomial F and G.
Yeah.
Look at all the roots of F. Take the product of G on those roots and take the product of F on the roots of G, and they're going to be the same on two signs.
Yes. Yeah. It's not very difficult. It's just, yeah.
So imagine then factor into linear terms, you can kind of see if you end up with the same linear terms of two multiple sections.
Yeah. If you look at this formula that Shanthanu has here, if you expand this G about I, it's like for each of I, it's product of I minus beta J. Product of all of J.
Yes.
Yeah.
Yes.
Another way to see this is in that determinant you showed you. Taking resultant of G comma F is just you take a bunch of columns, move them past everything else. So you pick up a sign change. That's it.
Yeah. Thanks. Yeah. And this formula is nice because in this formula you can see the resultant is actually an indicator function sort of thing. So if f and g did share a common factor, then it's clear that resultant of f and g will be 0 because one of those g of alpha will be 0. And if they don't share a common factor, then all of g of alpha will be non-zero. The product will be non-zero. So it's sort of nice to think about. Okay. So now we have the resultant, and we have two formulas for it. One is in terms of the coefficients of f, other in terms of the roots of f. Okay. And now we try to play this game. So now we do visual thinking. We say, okay, let's say I have access to the roots of f. Can I get a small circuit for this, small constant depth circuit for this? And then worry about, okay, how to actually get circuits over this coefficients. We'll see about it later. So we'll do the first step. So given the roots of alpha, can I get a constant depth circuit? And that is actually not that hard to see. So maybe I'll be explicit about it and give you a circuit. So if I'm given roots alpha 1 up to alpha m of f of x, so first what I would like to do is I would like to compute, let's say alpha 1 at g of x. So what I would do is, given an alpha 1, I can have some multiplication gates to compute all the powers of alpha 1, and then compute all the corresponding coefficients with the multiplication gates, and addition gate at top to compute the polynomial. So, okay, I was a bit fast there, but I hope that was fine. So I have a simple polynomial evaluation circuit of constant depth that takes coefficients of G, alpha 1, and computes G of alpha 1. I take multiple copies of these and multiply them at the top. The depth doesn't increase by much because I stack them side by side. So we can do this so we can compute the resultant of f and g given the roots of alpha into alpha m in constant depth, right? So we'll just maybe one more thing I want you to notice here is that this circuit I have, it is symmetric in alpha s. So that formula there, I can rearrange the alphas and the formula doesn't change, right? So we'll just note that, put it down in the slide. So the resultant is, so we get a depth first circuit for the resultant, given the roots. It is symmetric. And now the question is, can we get an equivalent circuit in the coefficients? Okay. So now I'll tell you, let's see. Okay. So now I'll tell you what is it that Anders Wigderson do here. So we had a circuit for it in the roots, and we want a circuit that takes the coefficients. Note, remember that I said that the coefficients are essentially the elementary symmetric polynomials in the roots. So what I want is, I want a circuit over the elementary symmetric polynomial over the roots, right? And what AW do here is, they notice that, so inspired from Eric's work, they noticed that, okay, suppose we were given the power symmetric polynomials over the alphas, then we can do this. Okay, so let me be explicit. Like, this was very fast. So this is what they do. So we have access to f0 to fm minus 1, which are the elementary symmetric roots in the roots. Using Newton identities, we can get access to the power symmetric polynomials. So the Newton identities lets us convert between given the elementary symmetric polynomials over a set of variables, we can get the power symmetric polynomials. And then from the power symmetric polynomials, using like BFSS, like from inspired from Eric's work, we get the resultant. This is
Are all these constant?
They're all constant depth. Yeah. And so this is how, so I'm not told, there's a lot of details I'm not said here at all, but this is the very high level picture here. And okay, this is amazing, but turns out the Newton identities does not hold in low characteristic. Those formulas don't hold. So this technical breakdown, if I'm in the regime of the characteristic being small, that is in particular being less than the degree of the polynomial I'm working with, then this idea fails. Okay. So now it seems like I have a copy of slide files. It's okay. Right. So now let me propose a different way to do this. Yes. If Newton, okay, let me phrase it like this. Suppose Newton identities did work over all characteristic, we would be done. Like this would work. Yeah. Okay. So let me now propose a way we go over it. So we'll look at a technique that will work over all characteristics, and the technique is sort of nice and might be of independent interest also, like apart from the context we are in currently about GCD and all that. So let's look at this problem I'm talking about the resultant a bit more abstractly. So what is it that we had? So I had a circuit for the resultant, which was constant depth, but took the roots of f of x as input, right? And somehow from this circuit, I want a circuit that instead takes the coefficients of f as input. And the coefficients of f are essentially the elementary symmetric polynomials. Okay. So now let's take a step back and reformulate this problem in a higher level generality and see if that helps. So forget the resultant and all that. Let's say I have a circuit that takes x1 up to xn as input and is constant depth and poly n size and computes p of x1 up to xn. And suppose it's symmetric in x's. So this is what we were in the resultant case also. We had the roots here, so it was symmetric in x's, and we had a constant depth circuit. So we just sort of generalized the problem now. All right. And what I would like is, I would like another circuit that is constant depth. Let's say that computes some other polynomial q, such that if I feed it in the elementary symmetric polynomials in x's, it will compute some q composed with those elementary symmetric polynomials, and that will be the same polynomial I had computed in the left side. Is that okay? So this is what I would, yeah. So if I could prove this statement, like if given an arbitrary polynomial p, if this is true, then the resultant immediately follows. The resultant is exactly this sort of thing. Okay. But in here, I seem to be implicitly assuming some things. In particular, what I'm assuming is, so forget all the the things about like circuits and all that. So I have a symmetric polynomial p, and somehow I'm saying that there exists a polynomial q such that q composed with elementary symmetric polynomials is p. So a priori, it's not even clear if such a polynomial q should exist, right? I mean, there's no good reason why it should exist. So this turns out to be true, and it's like a very old theorem known as the fundamental theorem of symmetric polynomials. I think it's proved by Gauss. So what this says is that if p is a symmetric polynomial, then there's a unique polynomial q such that p is equal to q composed with elementary symmetric polynomials. Okay, eSym1 is E1, eSym2 is E2. Okay, I might have used two different notations. Sorry about that. And that's kind of a nice theorem. Okay. Okay. Now that we have this theorem, now we can start asking questions about the complexity of computing Q and complexity of computing Q. Okay. So since we have this theorem now, we ask, what about the complexity of computing Q? Like if I had a small circuit for P, can I say something about how large a circuit for Q would be? You can ask questions like that now. And this was a result of, so this was proved, this was like, turns out like we can say something very interesting here. So a result of Blazer-Jindal says this. So the setting is same, just that P of X now is a symmetric polynomial and it's computable by, let's say, a circuit of size S. Then Q can be computable by a circuit of size Pauline S, D. Good question. So Blazer-Jindal doesn't say anything about the depth, but I mean, regardless of the depth, this is still an interesting statement, right? Right. And what we show is that this result is true is also depth preserving. So suppose P of X is has a circuit of size S and depth delta. Then Q of X has a circuit of size Pauline S, D, and the depth is a very small blow up in depth. I wrote delta plus 10 there, it's some small constant, whatever it is. And the typical regime of parameters we have usually is in applications of this theorem. Usually, if n is a number of variables we're working with, the degree and the size will be polynomial in n, and the initial depth of p will be some constant, let's say phi. Then the resulting polynomial q will also have size poly in n, and depth will be a small blow, constant depth blow. This is the regime you're interested in. Okay. And so our proof is essentially very similar to the proof of Blazer-Jindal. The main ingredient here is that an earlier, like a previous result, the same set of authors says that, so there is this fact that, so if you look at factors of small constant depth circuits, so if you have a constant depth circuit, and if you look at a factor of that polynomial, can we also say that that factor is a constant depth circuit? So we proved that result, and that turned out to be a crucial ingredient in extending the Blazer-Jindal result to constant depth circuits. Okay. And let's just complete the argument. So let's just see that once we have this theorem, we essentially have resultant and GCD also almost. So resultant we saw is we have a constant depth circuit for resultant in the roots, and this immediately gives us a circuit for the constant depth circuit for resultant in the coefficients, because the coefficients are just elementary symmetric polynomials. Like, it's very immediate. And for GCD, so I will not talk about how we'll do GCD exactly. So for GCD, what we do is we first build some. So given the roots of alpha 1 up to alpha d, I'll try to build. Oh, sorry. Yeah.
Somehow I thought in the beginning of the talk, what were the size of the circuit like roots and
It was poly. Okay, I have used n and d for degree, like interchangeably. It's poly in n.
poly?
Yeah, if n is a degree, poly n. Yeah. Initially, I think I used d to be the degree and said poly d.
Yes.
I've used n and d sometimes interchangeably, and yeah, I think that's the confusion.
Yeah.
Yeah.
It's poly n.
Poly n. If the number of input is number of variables.
Poly n and constant.
Yeah. Yeah. Okay. For the GCD, what we do is we first build piecewise symmetric circuit for GCD, given the roots. If suppose I assume that I have access to the roots, and then we apply the theorem we had to get in the coefficients. So this slide is glossing over a lot of details that are there, but the ideas are key ideas are here. Okay. So I have about 20 minutes. So maybe I'll try to prove this theorem. So this theorem seems to be the crucial ingredient in the whole argument. So we'll try to see the proof of this. Okay. So what is it I want? So I know that P has a small constant depth circuit. I want to show that Q has a small constant depth circuit. Right. So this is a setup. So I know that P of x1 to xn is Q of E1 up to En. So suppose there existed some algebraic functions, or let's say algebraic functions A1 up to An, such that the ith element is symmetric of these A1 up to An is xi. Okay. Then if I substitute A1 up to An, if I compose P with A1 up to An, it's equal to Q of Q of E1 up to Q of E1A up to ENA. Just that's A bar just means that it's a tuple of A1 up to An. And since element EI of A1 up to An is xi, Q of that's equal to Q of x1 to xi. So suppose we had this A1. So what I can do is this. So what it means is that I'm able to get my hands on Q from P. So to make it explicit, so I had a constant depth circuit for P. I plug in A1, A2, An into its inputs, and that's equal to Q. We don't know. if A1, A2, AN happen to be polynomials, and let's say they also happen to be constant depth, then we would be done immediately. So we don't know what A1, AN, this is like wishful thinking. If this is a strategy, maybe it might work, may not work. Who knows? Okay. So with this intuition in mind, we'll try to find such A1 up to AN and see how much progress we can make. So we would like to find these A1 up to AN, which are functions of variables x, such that the ith element is symmetric polynomial is xi. So I'll encode this using an auxiliary polynomial. So consider this polynomial. So think of this as polynomial over the variable z with variables in x like pushed into the ring. So and notice that its roots are exactly what we are exactly A1 up to AN. Because the element is symmetric polynomial in the roots, it gives us the coefficient x1, x2 up to xn. Right? So if let's say I'm able to find the roots of this polynomial, I get my hands on A1 up to AN. Right? But it turns out that this polynomial is not very nice to work with. So if I evaluate this if I set the x variable to 0, we get z power n, which is not square free. And so in general, this A1 up to AN are some algebraic functions in XS. I would like them to be power series in XS because I can use some known techniques to extract them. Okay. Right now, it's not okay. Nice equation to work with. I hope that's a good enough justification. But okay. So what Blazar General do is they sort of work with the perturbation of this polynomial to make this idea work. So what do? They take some they take some distinct elements B1 up to Bn in the field and let AI be the ith element symmetric polynomial in Bi's. And they define a small perturbation in H. So they define H hat, which is basically each the coefficient perturbed by A1, A2 up AN. Now notice that if I evaluate H hat at x is equal to 0, its factorization will not be square free. So its roots now will be B1, B2 up to Bn. And since B1, B2, Bn were taken to be distinct, we have that this will be square free. And once it's square free, we can talk about power series roots of this, and it's nicer to work with. Okay.
At the beginning of the talk, you said I want my base field to be large enough.
This is one place where I'll need it. Yes. So okay, now given this, I'll try to lift a root, a power series root out of it. What does lifting mean? So I have that Bi is a root of this h hat when evaluated at x equal to 0. So since h hat is square free, I have that there is a power series root phi I such that the constant term of phi I is Bi and h hat of evaluated at phi I is 0. Okay. For those of you who are not familiar with this notation, it's not particularly nothing fancy is happening here. It's just yeah. So what did I have? I have phi 1 to phi n, which are power series roots of this h hat of x comma z, such that the constant term of phi I are Bi. And so I would like to work with approximations to this power series roots. We'll come to why it is that in like 2-3 minutes. So let me define phi I hat, which essentially is I just throw away the degree d plus 1 terms from phi I. So phi I is the power series in x variables. I throw away some large degree elements and I get phi I hat. Okay. And oh, I think I missed. Okay, it should be 25. So what our earlier result says that we have, so these phi I hats, we can compute these in constant depth. So what this says is that I can compute the approximations to this power series in constant depth. Okay, and this is what will be useful for us to get constant depth circuits for Q, the composing polynomial I said initially. So now let's complete the argument with this. So we have P of x1 to xn is Q of E1 up to En. Now in place of x1 to xn, I substitute the power series roots. So P of phi 1 up to phi n. Since they are the roots of this polynomial, on the left hand side, the element symmetric polynomial with the coefficients. So that gets substituted with this. So the right hand side becomes Q of x1 plus a1 up to xn plus an. Now if you compare, I hope this was okay. Now if you compare both the sides, on the right hand side you have polynomial degree at most d. On the left hand side it looks like you're composing p with some power series, so it looks like some infinite object. But since it's equal to polynomial of degree at most d, so this should be something of degree at most d also. So this equality holds even if I throw away large degree terms. Now I can take the mod that is there inside the piece. So essentially I can replace the phi 1s with phi hats. Okay, we did all of this. So what is the point now? The point is all these phi hats, they have constant depth circuits. The P has a constant depth circuit. This gives you a hand on Q, on a perturbed version of Q, but still a constant depth circuit on the perturbed version of Q. Okay. So to make it explicit now, so I had a P. If I feed it phi hat, all this approximation power series roots, what I get is Q of x1 plus a1 up to xn plus an plus some higher degree terms because it's modulo that. And now if I just substitute like the input is x1 minus a1 up to xn minus an, I get my hands on Q plus some higher degree terms. And these higher degree terms we can remove with some standard interpolation techniques, which I won't talk about. And for this interpolation also, we need the field to be large here to remove this, strip out these higher degree terms. Since phi hats are constant depth, P is constant depth, the whole thing is constant depth. Okay. Hopefully, I didn't lose many people, but yeah. So, okay. So we end at 1. Okay. So, I see. So I seem to have gone faster than I thought. So, okay. Maybe I will. Maybe I'll tell a bit about how we do GCD. So we have concluded the proof of Wigderson. So just to, since this is a good stopping point anyways, so we have completed the proof of Wigderson statement, like the constant depth version of it. And that implies constant depth circuit for resultant, also the GCD. Since we have some time left, we did not see the details for GCD. So maybe I will try to show some details for that now in the remaining time. So I have to go into some extra slides. So.
Wait, sorry.
Yeah.
Well, you said that the field size, just following up on Eric's question, right?
Yeah.
Field size needed to be bigger than 2D, but here you only used, all you needed was really just D, right?
The field size, like to do interpolation, I think the field size need to be quite a bit more. D is also not enough. Because so the higher degree terms, they might have degree D square also.
Oh, sorry, there's the interpolation step here.
Yeah,
okay,
the interpolation might take.
Sorry. Yes. Okay.
So I might need a lot of field elements.
That's right.
Yeah. Okay. So let me now just maybe, okay, talk about how GCD works. So we saw that the resultant, to answer to your question, the resultant can be written as alpha minus beta j. So we saw that the resultant is g of product of g of alpha I. So let's just, so the theorem that I showed, it applies to all symmetric polynomials. So let's just see some other symmetric polynomials for which we can apply it to. So the resultant is product of g of alpha I. In particular, it is the nth element symmetric polynomial. So we can ask, okay, why restrict ourselves to the nth element symmetric polynomial of this g of alpha is? We can ask, okay, why not to consider these things? So what is the ith element symmetric polynomial of g of alpha 1 up to g of alpha n? So we saw that g of alpha 1 we can do in constant depth. It is known that right element symmetric polynomial is in constant depth. It is not a trivial fact. We know this, but so since we know that both of them in constant depth, we know that we can do the whole thing in constant depth. Okay. So what that means is that I can compute this expression. So this expression, in fact, if like I mean, it looks like an arbitrary expression, but this expression is defined in terms of roots of f. But somehow I'm also I'm claiming that I can compute this given the coefficients of f. So that is what is maybe slightly like nice about this statement. Like even though it's defined in the roots of f, I still say that I can compute in the coefficients. So it's kind of interesting. And but why am I talking about this polynomial at all? This is important for us to compute the GCD. So let's talk about computing GCD now. So I said that we have to work with piecewise functions for the GCD. I don't want to deal with those issues. So let's say I am promised that the degree of the GCD is D. Okay, this promise is given to me, and now I go to work on this. So let's only work on the square free case. Hopefully, I'll be able to finish it in 5 minutes. So we have f and g, whose roots alpha and beta I are all distinct. And suppose for simplicity, let's say alpha 1 is beta 1. Like since I assume that degree is d, so they share d roots. Both share d roots. Let's say like the roots are alpha 1 equal to beta 1 up to alpha d equal to beta d. So this notion of a filter will be useful for us. So what is a filter? A filter is I go over all the roots of f. Is this right? Yeah. I go over all the roots of f and I multiply x minus alpha wherever g of alpha is 0. And analogously, I define filter of f and g not equal to 0. Why am I defining these things? Turns out that the GCD is essentially, so the GCD of f and g is essentially filter of f when g equal to 0 as defined. And notice that that filter of f when g equal to 0 is essentially f of x per filter of f when g is not equal to 0 because they go over all the roots. So from now on, I'll focus my attention on computing this denominator. So once I get my hands on denominator, I can compute the GCD itself. So I want to compute this function. How would I compute this? So the idea here is essentially the same thing I mentioned. So we want to collect all the, so given alpha is, I want to evaluate g of alpha is at all point and collect terms which evaluate to non-zero. Okay. How do I do it algebraically? So I define an auxiliary polynomial h of x comma y, which is just g of y into x minus y. And notice this fact. So this polynomial which you saw earlier, it comes back. So what does this ECM I of g of alpha up to g of alpha n do? We'll notice that this acts like some sort of a thresholding function. What does that mean? If I is greater than n minus d, since exactly d of these are 0, any set of size greater than, if I take any set of size I greater than, which is greater than n minus d, I will take a set, I'll take a g of alpha which is 0. That's why it's always 0. If I is less than n minus d, it will be some non-zero value. I do not care. But what happens when I equal to n minus d? It turns out that that's exactly product of f of alpha and g this. So it exactly captures the product where f of alpha is not equal to 0. Did I make a mess up? Okay, this should be g, I think. Sorry, g. Yeah, it exactly captures the product when g of alpha is not equal to 0. Hopefully that didn't propagate. Okay. So let's now compute this esim n minus d of in the H's. This turns out to be esim n minus d, like h of x comma, if I substitute h value here, and so we get this. So since esim of n minus d is like actually a thresholding function, it exactly captures the value where g of alpha is non-zero. I think this keeps propagating. So okay, just so that I am also not lost, what is the objective here? The objective here is to compute the filter function. So we need to get our hands on the filter. The filter operation essentially is this product with just this term. This term was not there. So we'll try to get our hands on that. So once you separate these things out, yeah, it turns out that this expression esim n minus d of that, those h's, will be esim n minus d of this g's with the filter operation. So, okay, this is a long preamble of what I said. What I wanted to say, what I wanted to convey was this. The filter operation, which was important to compute in the GCD, is a rational function in elementary symmetric polynomials in the h's and the g's. And we know that we can do the right hand side in constant depth. Hence we can do this in constant depth. So we can compute the GCD in constant depth. This is what I think I might have lost a lot of you in the last part, but this is I think this is a good point to stop. Maybe I'll conclude with some and the result, and this only applies for the square free case. In the general case, we need to add some things, but it's okay. I mean, this is all the ideas we need. So let me now conclude with talking about some open questions. Okay. So we saw that we had a constant depth structure with GCD, and as you notice that the number of processes or the nodes were poly D. So now I can ask, okay, I can be a bit more greedy and okay, I have constant depth circuits. I also know that I have near linear size circuits. Can I get both? Is that possible? So we don't know this. And if we had known a fine-grained version of the Wigderson statement, if the statement said that if P had a size, so we remember the P and Q polynomial in the statement. If P had a size as circuit, if it said that Q had a S log S circuit or something like that, that would be sufficient for us to prove the first statement. So yeah, so that is a interesting open problem, and maybe I think I have not mentioned it here. I think we also, so in Anders Wigderson, they were able to show in the large characteristic case that given a polynomial, they can compute the square free part of the polynomial. Okay, the techniques we have here in the small characteristic, we are not able to show that. So these techniques will not. So that's also a nice open problem. Yeah, I can't remember anything else. So yeah, okay, thank you.
Is there a reason why these kinds of results should hold over small fields like F2?
Sorry, sir, I couldn't catch.
Is there a reason why these sorts of results should or shouldn't hold over F2 or other small fields?
I think it has more to do with the techniques than anything else. I don't know. I'm not sure how to answer that. Like it seemed like in AW, the reason it didn't hold over small fields was just over small characteristic fields was just because. Sorry, your question was about small fields or small fields. So if the field is too small, then would it be cheating to just work with the extension field? I think if you work with the extension field, make the field large enough, you should be happy. So the issue it didn't work here is that in the proof I had to take some distinct elements and work with it. But I believe if the field is too small, you can work with an extension field and pretend like you have like working with the representation of the extension field. You can still pretend like you're working over the small size field. I don't know if that makes sense at all, but
Okay.
yeah.
Does this mean that your actually works on any characteristic only that it has to be large enough field?
Yeah, I mean, I've thought about it a bit. I had a feeling, okay, this is nothing concrete. I had a feeling that it should apply over all fields. Like if the field is small enough, like how does a FP per k, how does FP per k work? I mean, it's like I take some polynomial of degree k and go modulo some degree k irreducible polynomial. Now, let's say you give me FP and that was too small for me. So I go to FP per k and instead of working and I build a circular FP per k, now the constants come from FP per k, but now I look at it as a polynomial of degree k and do make sure that the field operations are all in FP. I don't know if that made sense, but I think that might work, but it's not concrete, so don't hold me on to it.
What you can, but then, yeah, then the question comes, okay, how do you build the extension you want there?
Good question. You need access to a irreducible polynomial for that. So, okay, I guess I can say existence, but with randomness maybe, but okay.
Maybe more about the general construction. So that's kind of impressive because so you have a pretty large group there of size factorial n, and you're able to you have a very polynomial, and then you can write it in terms of some generating polynomials for the equation. And with a small overhead, which is theoretically inside of it. Are there other groups where these kind of things?
That is a good question, and I know that people have studied this. I cannot remember any references right now, but I believe that this is studied. That's all I can say. If anyone else knows in the audience knows more about it, please feel free to ask.
Let's think Shanthanu one more time. Shanthanu is around for the rest of the week, so if you want to continue to chat with him, feel free to email him or get in touch with me. I'll put you